Alrighty, everybody. All right. I am going to, in this session, I'm going to go over Unit 6 quiz and Big Idea 2 practice test keys. So let me start with Unit 6 practice quiz. And in Unit 6 practice quiz, the big topics there were Lewis structures, VSEPR, polarity, hybridization, and a little part of that was chemical bonding, macro and micro level, and alloys. So here we go. I'll be doing all of the questions, and I'll timestamp it so you can look over the questions as you wish. Okay. So here is question number on quiz 6. It says formic acid, which is given as HCOOH, and you have to always remember to complete the octet. Sometime a question may not give you completed octet, like in this question, oxygen's octet wasn't complete, so you must complete before answering questions. So A said, what is the hybridization on carbon? So around carbon, there are three electron domains. Remember, VSEPR treats single, double, triple bond as one electron domain. And because there are 3 electrons domain, the hybridization is sp2. It needs 3 hybrid orbital, and sp2, one of s and 2 of p's gives you that. What is the bond angle around around carbon? So the bond angle here is 120 degrees. And then they say, given the following structural formula, compare the relative strength of CO, single bond O, and C double bond O. C double bond O is stronger as compared to C single bond O. And as a side, remember C double bond O is shorter in length than C single bond O. Question number 2 asks you, what is the hybridization on nitrogen on each of the following? NO3 minus nitrate and NO2 minus. So nitrate structure is like carbonate. You come up with 4 bonds, and when you draw its Lewis structure, it comes up like that. And you will obviously have resonance here, and you'll draw all the 3 resonance structure if you were asked Lewis structure. But because they're asking hybridization, I can leave it here. And because there are 3 electron domains, hybridization is sp2 in this case. And in nitrite, NO2 minus, structure is N, lone pair on this end, double bond O, single bond O, and with a negative charge. And around this nitrogen atom, there are 3 electron domains again. So the hybridization is still sp2. Question number 3 says butadiene, and they have made the structure HC, double bond C, single bond C, double bond C, H, and a H here, and a H here, and a H here, and a H there. How many sigma and pi bonds are there? So every single bond is sigma. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 sigma bonds, and this one is a pi, and this one is a pi, and 2 pi bonds in here. Question number 4 says, use simple structure and bonding models to account for each of the following. A, the bond length between 2 carbon atoms in C2H4 is shorter than C2H6. So if you draw C2H4 structure, it looks like this, and C2H6 structure looks like this. One note for organic molecules is that each carbon atom must have its valency as 4. So if you look here, you are comparing a double bond to a single bond. So C bond in C2H4 is a double bond, and in C2H6 it's a single bond. Hence, it is shorter in ethene than in ethane. Part B of this question said that NH bond angle is 107.5 in ammonia, and again you justify it by drawing the Lewis structure, and you realize because there is a lone pair on nitrogen, it pushes down on these bond angle, and instead of the tetrahedral 109.5, the bond angle is 107.5 degrees. So the answer is because of the lone pair on the central atom and because of greater repulsion between a lone and a bond pair, the bond angle gets scrunched. Part C, the bond length in SO3 are all identical and are shorter than sulfur-oxygen single bond. So if you draw SO3, I think you get a double bond, and when you have a traveling double bond, remember it is resonance structures, and as you do that, you have 3 resonance structures for this. And now you know that the bond order here will be, if you take any 2 positions, there are 2 bonds here, 1 bond here, 1 bond here. So total 4 bonds in 3 structures. So its bond order is 1.33, which goes to say that the bond is shorter than a single bond because it's between a single and a double bond. Okay. And I will go to D, but I see some of you are here, and Dan has a question. How do we justify the strength of a single versus double bond? So you can say, because in double bond, it involves sharing of 2 pairs of electrons versus 1 pair of electron. The bond is stronger because of more overlap of atomic orbitals. The only specific bond angle values that you expected to know, Dan, are AB2E2 and AB3E. AB3 is 107 degrees and AB2E2 is 105. For rest all, saying that it is less than 109.5 or less than 120 is good enough. All right, moving on to part D of the same question, that is question 4. Why is I3 minus ion linear? And when you draw its Lewis structure, you'll realize this is the structure you get. You have 3 lone pairs of electrons on the central atom, and because the lone pairs are really part of the electron cloud of the central atom, if you look at the molecular structure, it's linear. So question number 4, you pretty much justify with Lewis structures. Alrighty, now on to question number 5. Question number 5 says, use principles of bonding and molecular structure to explain the following. The angle between NF bonds in NF3 is smaller than the angle between BF bonds in BF3. So when you draw Lewis structure of NF3 and BF3, when you go through your 5 steps, you realize that NF3 looks like that, but BF3 looks like that. Because of the lone pair on nitrogen, the lone pair bond pair repulsion is greater than bond and bond pair, and this bond angle, instead of being 109.5, scrunches to 107 degrees. But in BF3, there are no lone pairs on the central atom because boron is okay with 6 electrons in its outermost energy level, and that is why the bond angle here is 120 degrees, and that is why NF3 bond angle is smaller than BF3. B says, that was A, 5A. 5B says I2 is insoluble in water but soluble in carbon tetrachloride. And again, when you draw the bond of I2, you realize that there is a single bond between 2 I atoms to form an I2 molecule. And if you have another I2 molecule, then what bond is intermolecular here is LDFs. And between water molecules in water, what you have is hydrogen bond between them, right? And hydrogen bond is stronger than LDFs. Hence, iodine really is not soluble because it's not plausible that hydrogen bond between water molecules will be broken to form the weaker London dispersion forces. But I2 is soluble in CCl4, which is a non-polar solvent, because CCl4, between CCl4 molecules also, there is only LDFs. And then LDFs can attract each other. And that is why I2 is soluble in non-polar CCl4, but is not very soluble in water. Moving on to question number 5C. 5C says diamond is one of the hardest substances, and you have to justify it by saying that diamond has covalent network bonds. And in covalent network bonds in diamond, each carbon atom is joined to other carbon by covalent bonds. And because covalent bonds are fairly strong due to a good overlap, that is why diamond is a very strong substance. And 5D says HCl has a lower boiling point than HF or HBr. So HCl, between HCl and HF has hydrogen bonds, hence will have higher boiling point than HCl. If you compare HBr and HCl, you justify the HCl's lower boiling point based upon London dispersion forces between HBr molecules and between HCl and other HCl. Br being larger than Cl will have more electron cloud distortion, hence higher LDFs. And here you must notice, guys, that the question will lead you to answer. Sometimes it's asked me, should we justify based upon dipole, or LDFs? So this is an example of a question where you will justify this answer based upon LDF, because that's what leads you to the justification. Let's go to question number 6. Question number 6 on quiz 6. Explain each of the following observations in terms of electronic structure and non-bonding of compound A. Under ordinary condition, HF is a liquid where HCl is a gas. So HF is a liquid, which indicates stronger IMFs. And that is true because HF has hydrogen bonds. And in HBr, it's a gas, which indicates weaker IMFs. And that is true because here it is mostly dipole-dipole interactions. And because hydrogen bonds are stronger than dipole-dipole, hence HF is liquid while HCl is a gas. That was 6A. 6B, molecules of AsF3 are polar, where AsF5 are non-polar. So in AsF3, I think you have 1 or 2 lone pairs. I forgot, so you have to draw out the structure. And because of this lone pair or pairs on the central atom, the geometry of AsF3 is distorted. So the individual dipole between As and F do not cancel each other out. But in AsF5, it is a trigonal biplanar molecule. Right, bipyramidal molecule. And it's a symmetrical molecule. Hence, the individual AsF dipoles cancel each other out. So this one is non-polar and this one is polar. Okay, then see, the NO bonds in NO2 minus are equal in length, whereas they are unequal in HNO2 minus. So NO2 minus's structure is like that. You have N, lone pair on it, double bond O, 1, 2, 3, 4, single bond O, 1, 2, 3, 4, 5, 6, right? But if you draw H and O2, then what happens is this double bond becomes a single bond. You have H, N, and then O, and this, right? So now the question here asks, NO bonds in this are equal in length when they are unequal here, right? So here they're equal in length because it shows a resonance structure. So this double bond travels between two NO atoms, and because of this movement, electrons are delocalized and traveling. Hence, the bond order is 1.5, right? It is the same. So every bond is the same. But in this case, NO bond and OH bond length will be different because the atomic radius is different, right? Between N and O and H. Then part D says, I'm going to erase this. And part D of this says, for sulfur fluorides, SF2, SF4, and SF6, these are known to exist, but only OF2 for oxygen exists. That's because sulfur can expand its octet due to the presence of d orbitals present in third period. Third period on, you have d orbital. But in oxygen, which is in second period, there is no d orbital to expand the octet. Hence, you have only one OF2. Moving on to number 7. Number 7 says, using principles of atomic explained by lattice energy of CaO is negative 3,460 kilojoules per mole, while the lattice energy of K2O solid is negative 2,240 kilojoule per mole. So negative sign, guys, in chemistry means release of energy. There's a lot more energy released here, meaning this is a stronger bond as compared to this, which stands to logic because according to Coulomb's law, lattice energy is proportional to the charges on the ions and inversely proportional to the distance between them. And calcium and oxygen both have 2 plus and 2 minus, while this has 1 plus and 2 minus charge. And these charge differences lead to larger lattice energy for CaO, which is indicated in this released energy as 1 mole of this solid is formed. Why did HCl not ionic, and how should we classify it and its ion? HCl does not have a metal cation in it, right? Anything that does not have a metal cation in it will not be ionic, will be molecular. We classify HCl as an acid or a molecular compound, and its IMFs are dipole then. Okay, let's go to question number 8, which is MO theory, and they ask you, is this molecule likely to form He2? So if you remember MO theory diagram, well, you don't need to because it will be given to you. 1s orbitals form anti-bonding 1s and form a lower energy bonding sigma 1s. And then 2s, again, same thing. 2s orbital forms bonding, so sigma 2s. And then this is the 2s atomic orbital. And then it forms anti-bonding 2s. Okay, so if you are looking at helium, hydrogen helium has 2 electrons. So there will be 2 here and 2 here. So bond order is number of electrons in the bonding orbital. So bonding orbital is this one, which is 2 minus how many electrons in anti-bonding? 2 divided by 2, so that is 0. Because of 0 bond order, He2 is not likely to form. You're welcome. Okay, and then number 9 says use the following diagram to fill and calculate the bond order of N2. So I can show you, it'll be the same, the diagram before that, and I edited it because this diagram is for oxygen and fluorine that's given here. It's a wrong diagram, so you'll be filling in the diagram before. And nitrogen has 7 electrons, so you will fill 2 in 1s, 2 in 2s. You will fill 2 to 4, 1 each on these p orbitals, right? So you will have this filled, this filled, this filled, this filled, and 14. So 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So all of these will be filled. And to calculate bond order, number of electrons in bonding orbitals will be 2, 4, 5, 6, 7, 8, 9, 10. 10 minus, it has 4 in anti-bonding orbital divided by 2. So that's 3 bonds. And bond order is 3. So what does that mean? So not 3. So bond order is 3, meaning that yes, it can form and there will be 3 bonds between 2 nitrogen atoms. Okay. For the VSEPR geometry, will you care if you only... No, I will not care if you're only off by 0.5 degrees, whether you write 107 or 108, that's fine. All right, and number 10 here says, what type of alloys are represented in the following diagram? So if you look at the first diagram, it is showing substitutional alloy because the metal atom are about the same size. And the second diagram shows the interstitial alloy. And that was quiz 6 elements. Now moving on to big idea 2 practice test. So just a warning here, if you have not taken your big idea practice test, please pause this video here, take the practice test and then check your answers with the key. And if you're confused about a question, then you can look at this video. Okay, big idea 2 practice test. Question number 1 says, if the Lewis dot structure of NO plus is drawn as N triple bond O, and one here with the +1 charge, then the formal charge on atoms is, so if you calculate nitrogen formal charge, it's 5 minus 1, 2, 3, 4, 5, 0, and oxygen is 6 minus 1, 2, 3, 4, 5, plus 1. So the right answer is C, 0 on nitrogen and +1 on oxygen. Oh, I'm sorry, I did not see Dan's question. And Dan's question was about number 6. What different property you should have said? Did they ask you for property in that? Let me check. Compare their properties, yes. So Dan, in number 10, the properties would be that the second diagram alloy will be very hard and brittle because the interstitial spaces are occupied by much smaller atoms. So atoms cannot slide past each other. So there is not flexibility. While in the substitutional alloy, it will be a lot more flexible and less rigid. All right, so now I am back to practice test big idea 2. Question number 2. At 298 Kelvin and 1 atm, bromine is a liquid with high vapor pressure. High vapor pressure means it's got low intermolecular forces because it can go in gas phase that exerts force on the surface of liquid. So if this is bromine liquid, some of it evaporates and this gas causes a pressure on the surface of liquid that is called vapor pressure. So high vapor pressure means low intermolecular forces. And so bromine is a liquid and chlorine is a gas. So liquid means they are stronger IMF. I'm just deciphering the question as going along. These observations provide evidence that under the given condition, the answer is A, Forces among Br molecules are stronger than among chlorine molecules because it is in liquid state and this is in gaseous state. Okay, question number 3. One property of metals that makes them different from other solids is malleability, the ability to change shape rather than fracturing into pieces when pressure is applied. Which of the following best explains why metals are malleable? Answer is B. Constantly moving delocalized electrons make metallic bonds non-directional, so the atoms can move in relation to each other without generating repulsion. 4 is based upon the diagram of BrF5 molecule. And there is a lone pair and all the octets are complete on the side atoms. Okay. And the answer is C because its molecular geometry is square pyramidal. Bond angle is less than 9 and 90 degrees and it will be polar. Okay. Question number 4. This gets too low. Let me erase it. Question number, oh, that was question number 4, sorry. Question number 5, they have given you the structure of tetrafluoromethane, which is CFFFF, and wow, that's one too many F's, huh? Okay, here I remember a joke, guys. It's kind of a brutal joke, but I'm going to say it. One of the kids brought his parents a report card and says, you know, my report card looks like carbon tetrafluoride. Haha, bad joke, huh? Okay, then trifluoromethane looks like this. It's got 3 fluorines and 1 hydrogen. And all the octets are complete, okay? And then they ask you, which of the following statements provides the best explanation for which two molecules will have the stronger dipole-dipole interactions with the polar molecule. So you're looking at the polarity. You know that this is a symmetrical molecule, tetrahedral. Even though there are individual dipoles, the net dipole is 0. But in this molecule, even though it is tetrahedral, there is no lone pair to distort geometry. This one, this dipole, is pointing towards carbon because hydrogen is more electropositive. So they don't cancel each other out. Hence, this will be a polar molecule. So this will be more soluble. And the answer here is D. Then for number 6, the melting point of MgO is higher than NaF. Answer is B, 1 and 2, both, because if you compare MgO with NaF, it is 2 plus 2 minus charge versus 1 plus and 1 minus charge of fluorine. Number 7 gives you formulas and ionic radii of some ionic compounds, and then they ask you which matches their boiling point. So if you look between BaO and you look at BaS and you look at MgO and you look at NaBr and you look at NaCl, there are 2 factors acting, charge and radii. So this is plus 2 minus 2 plus 2 minus 2 plus 2 minus 2 plus 1 minus 1 plus 1 minus 1. So you know these 3 will have higher lattice energy. Now how do you decide between these 3? You look at the size of the atoms. This is, Mg is smaller, right? So this one will be strongest attraction. This one will be second highest, third highest, then fourth highest and fifth highest because bromine is larger than chlorine. And given that, your answer is D. So you're looking at ions and you're looking at charges. Continuing on now on to free response section of the practice test. Question number 9 says, using particulate level drawings, explain the bonds broken and formed when bromine dissolves in water. So bromine molecules are covalently bonded, non-polar covalent bond, and the bonds broken when bromine is dissolved in water. So bromine is interacting with each other through LDFs. Water molecules are interacting with each other through hydrogen bonds. So bonds broken are LDFs and hydrogen bond. And when it dissolves, the bromine will interact through LDFs and through polarization. So if I draw this side to be slightly negative charge, this side to be slightly positive charge, the temporary dipole, then the hydrogen end will attract it. So this will be LDFs. Okay. Question number 10. 10A says, using VSEPR theory to predict hybridization on, so look at pictures here. There is propanoic acid, CCCOH, double bond O, H. So 1, 2, 3, 5, 6, 7, 8, complete octet. 1, 2, 3, 4, 5, 6, 7, 8. Guys, always watch for octet completion. Now they say predict hybridization on C1, C2, C3, and then I have gone on counting, so 4, and then methylamine goes like that. So NH2 is like that, guys. So there's a lone pair here as well. And this is 4th, so I've labeled this 5th, 6th, even though it's not the same molecule, just for you to understand which atom I'm talking about. So they ask you for hybridization on C1. There are 4 electron domains around it. So C1 is sp3. C3, 1, 2, 3. 3 has 3 electron domains, so C3 is sp2. C4, no, O4. O4 has 4 electron domains again, so C4 is sp3. And C7 is 4 electron domains, is sp3. And nitrogen, again, has 4 electron domains, so it is also sp3. Then B asks you, determine the bond angles and electron domain geometry around C in C double bond O in the first structure. So what is the electron domain geometry and bond angle? So there are 3 bonds around it. So bond angle is 120 degrees and electron domain geometry is trigonal planar. Remember, it's a planar molecule. Okay, part C of it says, I am doing 9C. A student claims that propanoic acid and methyl ethanoate are 2 appropriate structures for propanoic acid. So CH3, CH2, C double bond O, OH, and the other structure is CH3, C double bond O, O, CH3. This is methyl ethanoate, and this is propanoic acid. And now the question says that, are these 2 appropriate structures for propanoic acid? Use your understanding of formal charge. So if you look at your formal charges, when you calculated, the formal charge on each of the carbon and oxygen atom in the center is 0, 0, 0, 0 in each structure. Hence, both of these are appropriate Lewis structures. Part D asks you how many sigma and pi bonds are in propanoic acid. So every bond is sigma, but other is pi. So let me write expanded structure. CH3 means this, right? CH2 means this. I'm going to raise the formal charges, CH2. OH, right? So now let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's got 9 sigma and 1 pi bond. What intermolecular forces will exist between molecules of propanoic acid? It will be hydrogen bond and LDFs because there is a OH here. So for E, if you just said hydrogen bond, that's fine. If you said hydrogen bond and LDFs, that's fine as well. And E says propanoic acid is fairly soluble in water. Using particulate level drawings, explain what kind of intermolecular forces will exist between propanoic acid and water. So propanoic acid is this. If there is a water molecule, you can draw it as HOH because we've drawn it as the structure. So if we do O, too big O. If we do O, H, H, lone pairs, slightly negative charge, slightly positive. This bond here will be hydrogen bond, and that will be F, answer for F. Okay, my laptop has low battery. Let me go grab the charger, guys. I'll be right back. Okay, I'm going to move to the side of the board. Okay, so then the next question here is number 11 that says ethene may be prepared by dehydration of ethanol, molar mass this much, using a solid catalyst. An experimental, the setup for this is shown. And A says use the Lewis dot diagram or draw Lewis dot diagram for C2H5OH. When you draw these guys, the only trick is to remember each carbon has 4 valencies and you must make sure they have 4 valencies or complete octet. So that is the electron dot diagram for C2H5OH. Approximately the COH bond angle, there are 2 lone pairs, so it's AB2E2, so it's 105 degrees. That is B. C is what is the hybridization around O atom in COH bond? Hybridization, there are 2 lone pairs, 2 bonded pairs is sp3. D, during dehydration experiment, C2H4 and unreacted C2H5OH passed through the tube into the water. The C2H4 was quantitatively collected, but the unreacted C2H5OH was not. Explain this observation using IMF. So C2H4 is a non-polar molecule and it does not really dissolve in water. But C2H5OH forms hydrogen bonds with water. That's why it's soluble in water and it cannot be collected. So when you're collecting something, it's really not soluble. There's a question from Brendan. How long will the actual test on Friday be? When it is 45 minutes and or 5 minutes collection and distribution. And the length is exactly the same. There are 11 questions, I think, or 12. I think there are only 11 questions. As many as on practice test is the same number of multiple choice and free response. Okay, then part E goes to the gas stoichiometry. It says a student added 0.2 grams of C2H5OH liquid in a test tube, and they heated the test tube gently with a Bunsen burner till all of this C2H5OH was evaporated and gas stopped forming. When the reaction was complete, the volume of collected gas was 0.0854 liters at 0.822 atm, that is the pressure, and temperature is 305 Kelvin. The vapor pressure of water is, this is P total. And vapor pressure of water at that temperature is 35.7 torrs. And they ask you to calculate how many moles of C2H4 are produced. N is equal to RT over PV. So R is 0.0821 liter atmosphere per Kelvin mole. Temperature is 305 Kelvin. P, you have to, oh goodness, I am tired. I switched them around. PV is equal to nRT, right? So PV over RT, and this pressure has to be of C2H4, right? So you subtract from total pressure the vapor pressure. So from H22 atm, you subtract 35.7 divided by 760 atm, right? You have to convert it. Volume is 0.0854 liters. R is 0.0821 liter atmosphere per Kelvin mole. T is 305 kelvins. And when you do that, you get the moles of C2H4 as 2.64 times 10 power negative 3 moles C2H4. Oh, you can't see that. So answer is 2.64 times 10 power negative 3 moles C2H4. Okay, then the next part of it is II, and they ask you that are actually produced if this went to completion. So how much grams, 0.200 grams of C2H5OH we took, right? And you convert it to moles by dividing it by 46.1 grams, and then you get 0.00434 moles of C2H5OH, and dehydration means they remove water. So if you remove H2O from here, then you make C2H4. So you know it's a 1-to-1 mole ratio. Right now, I will give you this question, this equation, but by the time you write AP exam, you should be able to do this on your own. So you know these many moles of C2H4 mean same moles of C2H4. Now, using those, so they only asked you the actual moles, right? So these many moles will actually be produced if the reaction went to completion. And then in part B, they ask you for percent yield of C2H4. You know percent yield is 2.64 times 10 power negative 3, which is actually produced over 4.34 times 10 power negative 3 times 100. And that gives you a percent yield of 60.8%. And that is the end of this practice exam, guys. I know 4 of you are listening. So thank you for attending this session. For rest, I'll timestamp it and put it on Facebook group for your benefit. Thank you, everybody, and you'll be okay.